Well, here we go, chapter 5.4. You'll notice that there is a tie-in here to Appendix 803. What we're doing in 5.4 is something that's very lab intensive. All right, you are going to actually make these solutions. Now, unfortunately, this is not something that we can do in a Learn From Home model. So we will have to cover this off at some other point when we get into titrations and things like that in Chemistry 30. But you should be able to figure this out. It really is just stoichiometric. A couple of terms that we need to pay attention to here are standard solutions, and simply said, these standard solutions are ones with accurate and well-known concentrations. All of this is in page 803 of your textbook. Standard solutions become very important for us in chapters 7 and 8 because we will use them in a very precise form of stoichiometry called titration. So if we're ever asked to make one, we must measure very precisely. Now we can do this from a solid, in which we have looked at questions in the last chapter, or last part of the chapter in 5.3, on figuring out what mass of solute was needed to make a certain concentration. So we've kind of already done this. All right, to save a little bit of time, we're just going to move on from there. I will do the example associated with it, and you'll see how similar it is. All right, but ultimately, we just need to concentrate on something we haven't really done a lot of, and that is preparing a standard solution by diluting a stock or other standard solution. So this is a dilution formula and really just a ratio by changing volumes. So a standard solution is prepared by diluting the existing stock solution. Stock solutions are generally very highly concentrated, very expensive, very reactive, very dangerous. So we tend to like to use much more dilute solutions whenever possible. To do this, we are going to take a very well-known volume and dilute it into another very well-known volume. To take our stock solution, we use something known as a pipette. This volumetric pipette right here only has one little mark on it to tell you an exact, very well-known volume of solution that is in there. These volumetric flasks, again, only have one mark and allow us to know a very well-known and precise number for the amount of solution that we have. In other words, we're using special glassware in our dilution so that we can get many more significant digits. All right, that's all that's going on with the pipette and volumetric flask. All right, it's all described on page 803 if you want to take a closer look at it, but it boils down to a ratio. All right, we can do this very much like we did with all those gas law ratios. This is a formula you'll want to memorize, but realize that the amount of moles that I have of my solute in the pipette, even though I've transferred it into this flask, is going to be the same even when I top it up with water. So, since concentration and volume, moles per liter, times liters would just be moles, we can extend this idea that the moles of one solution, the pipette, will be equal to the moles of the second dilute solution, the flask. So, usually this will be your pipette, and this here will be your flask. All right, so we have new concentrations because we are changing the volumes. So again, factor label method is awesome, it's wonderful, but when it comes to just dilution ratios or direct and indirect ratios like we saw in gas laws, it's easier to memorize the formula. So while factor label method could be used in all situations, sometimes it's easier to use and memorize a formula. Let me show you what I mean. All right, this one here is just preparing it from a solid. I'll come back to that one in a moment. Let's go straight to this dilution one that we're talking about here. All right, so if I want to dilute a solution, all right, 10 mils of a 0.15 molar solution diluted to 100 mils of total volume, it's really just my dilution ratio. And when you think about this, I have an initial solution and I have a new solution. Read the question. Which one is the initial solution to you? For me, it's the 10 mils of the 0.15 molar. Okay, so I'll plunk that in. I have a 0.150 molar concentration, and I have 10 mils of it. That means I'm trying to calculate the concentration, C2, of my new larger 100.0 ml volume. How would I solve for this one? Well, now it's just simple algebra. I need to get C by itself, so I'll divide both sides by 100 mils. You can see mils cancel, and I'm just left with a mole per liter concentration. So, as we finish that off, we just have to run this through our calculator, and we get our calculator spitting out 0.0150 moles per liter, being equal to the new concentration. All right, if gas laws and Boyle's and Charles' law were all working well for you, this dilution equation should be very simple for us as well. Okay, here we have another one. It's got a little wrinkle to it. All right, we talked about this earlier. We do have a table on our data sheet that talks about commercial reagents. All right, as we take a look at this second example here, the volume of commercially produced hydrochloric acid, it says C data sheet, required to prepare 2 liters of a 0.1 molar solution. All right, we want to take a look at what we're doing, the procedural steps. Again, if we were in lab, that would be something much more important to talk about, but we really don't get a chance to work with it. So let's just see if we can get the numbers. All right, we need to find our commercial hydrochloric acid. And so there's your typical commercial reagent solutions. There's hydrochloric acid. And when we buy this, it has a molar concentration of 11.6 moles per liter. So our concentrated hydrochloric acid has a concentration of 11.6 moles per liter. All right, now we have our dilution. C1V1 is equal to C2V2. I would assume that our concentrated hydrochloric acid, okay, is the initial solution. Our dilution is the second solution. Doesn't matter if you do it in reverse, it'll all work out, but I have 11.6 moles per liter, and I'm looking for the volume necessary if I try to make a 0.100 mole per liter solution and a 2 liter volume. So to get the volume that I need, I divide by 11.6 moles per liter. Do that to both sides. You can see moles per liter cancel, and I'm left with a volume in liters. So V1, when you run it through your calculator, should be 0.0172 liters in our 3-digit limit, or if you prefer, 17.2 milliliters. All right, dilution equation, pretty straightforward. Okay, I will come back to this one here. Again, we've done questions like this already. We're just being asked to figure out a mass, and remember, we have a molar concentration that helps us out. So, if I want to prepare 100 mils of this solution, what mass do I have to weigh on a scale and dissolve in 100 mils? For this, again, a good starting point is my concentration. And that would be my zinc sulfate heptahydrate. And then from here, all right, I want to cancel out those liters and just get to grams. And so my liters, 0.100 liter solution is what I'm trying to get to. And now I just have to get from moles to grams. There's moles, there's grams. This is a fairly big one to weigh out, but if you count for all of those atoms in this crystal, for a 1 mole quantity, you get 287.60. Moles cancel, and now you're left with grams, and it works out to 8.63 grams of your zinc sulfate heptahydrate weighed out on a scale when you correct sig digs. Okay, won't see anything like this directly. We did stuff like it already in the previous chapter. I'm not going to relate it to procedural dilutions. The ones you want to know are the C1, V1, C2, V2 formulas. All right, so when you're going through here, all right, the questions on page 216, not really necessary. Stick to the ones on 218 and 219. Those deal with your dilutions. And again, we're not doing any of these labs. All right, that's 5.4. We'll talk about one more thing. All right, there is chapter 5.5. This is dealing with some very specific stuff here on saturated solutions. We don't deal with saturated solutions going forward in Chem 20 or again in Chem 30, so we can ignore that. Solubility changes based upon temperature. It's a very obscure thing. Again, it's not something that we are going to do in Chem 30, so it makes sense for that to disappear. Solubility in water, some generalizations. Doesn't hurt to read this, but you won't find any particular questions on it. And then this is something that will come back to us in Chemistry 30. So I have to reteach this exact same thing in the equilibrium unit of Chemistry 30, right down to the exact same example. So why not save it for then? Because it's a little bit confusing to get through. All right, so don't worry about the question assignment here. Don't worry about Lab 5C, but your Chapter 5 summary questions and review are on page 230 and 233. Try some of those. If they're getting to saturated solutions and things like that, obviously ignore them, or if you wish, you can certainly read through this. All right, just realize that what I'm canceling out will never appear on your quiz. Okay? Doesn't mean that it's not good content. There you go, guys. That's Chapter 5 in its entirety. You'll start to see Chapter 6 videos starting to appear near the end of the week, and your Chapter 5 quiz will be next week. I think I have it set up for the 6th or the 7th as memory serves. There you go, guys. Good luck with everything. I will see you for our tutorial check-in on Friday afternoon.